Assalamualaikum warahmatullahi wabarakatuh. We are here today to present a group assignment for MAT 668, which is the graph theory. So, for our group assignment, we are choosing the green supply chain optimization for Federal Agricultural Marketing Authority, FAMA in Melaka, Malaysia. So, for our team members, we currently have 3 team members in our group assignment, which is myself, Amirul Fahmi Bisraji Fikri, Atika Sharafana binti Ismail, and Ernie Nadia binti Muhammad Sufyan.
Assalamualaikum. Today we are going to present our project on optimizing collection routes for FAMA Melaka. FAMA Melaka is responsible for collecting fresh produce from 16 farming areas across the state. Each farm has a specific time window for collection. This is important to ensure that the produce stays fresh and maintains its quality. The main goal of our project is to find the best collection routes. This will help reduce travel time and lower operational costs. To solve this problem, we use a method called the vehicle routing problem with time window, or VRPTW for short. The network we are working with consists of 1 depot and 16 collection hubs, making a total of 17 nodes. We have a fleet of 4 refrigerator vehicles. These include 2 3-ton refrigerator trucks and 2 5-ton terminal containment trucks. Each vehicle has a different capacity, so we need to assign them wisely. For data collection, we use Google Maps to get the exact location and distance between all the points. Then, we use Google OR tools in Google Colab to find the optimal routes for the vehicle. In the end, our results will help farmers improve their logistics, reduce costs, and ensure that all collections are done in time. Now, let's continue with the problem statement. Now, let me explain the problem that we are trying to solve. First, farmer needs to find the optimal collection routes. This means we must minimize the total travel time while making sure that all 16 agriculture hubs are visited within their specific time window. This is important to keep the produce fresh. Second, we need to minimize the total collection cost. To do this, we optimize vehicle allocation and routes planning. Since we have a different type of vehicle with different capacity and fuel efficiency, we must assign the right vehicle to the right route. Third, we want to identify the most suitable vehicle configuration. This means we need to determine which combination of vehicle works best based on capacity requirements and full cost optimization. These 3 problems are what we aim to solve this project.
Okay, next we will continue with methodology, or how to solve the problems in this case study. Okay, so first of all, we collect the data or data collection. This method is implemented so that we can have all the inputs that we're going to use later in Google Colab or Python. So firstly, we select 17 locations in Google Maps, which consists of 1 central farmer depot and 16 specific agriculture zones or farms in Melaka. So as you can see at the right, it is a figure of all of the 17 locations in Google Maps for Melaka. We then identify the node, location, coordinates, and label it for coding in Python. We also identify the data of times from start to end at each of the location, and then we identify the vehicle types, number of vehicles, and also its capacities. So for example, the nodes A is for our central farmer depot, which is Farmer Air Depot. So at Farmer Air Depot, the start time of delivery is on 6:30 am and the end time is also 6:30 am, so the duration is 0. Then we identify the vehicle types. Like in this case study, there are 2 types of vehicles, which are 3-ton refrigerated truck and 5-ton thermal containment truck. For the number of vehicles or the quantity of the vehicle used in this case study is 4, which are 2 for 3-ton capacities and 2 for 5-ton capacities. We also identify the full efficiency for each vehicle types. Like for 3-ton refrigerated truck, the full efficiency is 4 km per liter, while for 5-ton, it is 2.8 km per liter. Next, we will continue with the second methodology, which is to create an adjacency matrix of distance in kilometer. So it is shown here, the matrix of distance in kilometer for all of the 17 nodes from A till Q. And the last one for methodology is we solve it using vehicle routing problem with time windows, VRTWs, and also Google OR tools. We use the Python coding to solve this case study problem. Firstly, we code the possible route for all the 17 nodes from A to Q, and then we find the routes for 2 of the 3-ton refrigerated truck and the route for 2 5-ton thermal containment truck. So from this coding, we get the output of this distance matrix, the total distance, the total load, the total fuel cost, the total travel time for each of the vehicles, and also for overall. And also we get the output or figure of the road for each of the vehicles.
Okay, for our results, I will start by showing this network graph, which provides a visual representation of all potential routes used by the FAMA fleet. It maps the geographic relationship between the central FAMA depots and the 16 agricultural collection hubs across Melaka. Using the vehicle routing problem with time windows and Google OAuth tools, our goal was to find the specific combination of paths that gives us the suggested routes with the lowest travel time and distance. Okay, next we're gonna start presenting the 3-ton refrigerated trucks. To ensure the lowest travel time while meeting street collection windows, the system divided the routes among 4 trucks, which means 4 vehicles. Here are the 4 vehicles, which is the vehicle 0, 1, 2, 3. The vehicle 01 represent the 3-ton refrigerated trucks. The vehicle 23 represent the 5-ton thermal containment trucks. Here are the suggested routes for the one of the 3-ton trucks. Among the entire fleet, vehicle 0 was assigned the shortest suggested route, sequence A to D to E and back to A, because it covers only 17 kilometers. It has the lowest individual travel time and the fuel cost consumption is only 16 ringgit and 87 cent in fuel. Okay, next for the vehicle 1. Vehicle 1 handles a slightly longer route of 37 kilometers, following the sequence from A to B to C and back to A with a fuel cost of 36 ringgit and 72 cents. Okay, next we are going to present the 5-ton thermal containment trucks next. Next, we have the 5-ton thermal containment trucks, which handle the remaining hubs that require a higher collection capacity. For the vehicle 2, it covers the largest regional group, traveling 88 kilometers and following the route sequence from A to J to N to O to P to Q to M and back to A. The fuel cost for this route is 124 ringgit and 77 cents. Okay, next for the vehicle 3, it covers the remaining hubs across a 37-kilometer route, following the sequence from A to H to I to L to K to G to F and back to A, consisting 52 ringgit and 46 cents in fuel. By running all of these vehicles simultaneously on these specific paths, we ensure that the entire operation is complete in the lowest possible time.
Now, let me conclude our presentation. In this project, we successfully minimized the overall travel distance while strictly adhering to narrow pickup time window and vehicle constraints. By using the vehicle routing problem with time window and Google OAuth tools, we distributed daily collection across 4 vehicles to cover all 16 farmer cooperatives. We found 4 optimal routes that achieve a total flight distance of 179 kilometers and an optimum daily full cost of Rm230.82 ringgit. This routine approach helps minimize operational budgets, reduce fuel consumption, and prevent unnecessary delays in collection. Finally, the best route with the lower travel time is Vehicle 0, which follows the path A to D to E and back to A. This route covers 17 kilometers and takes only 48 minutes. In conclusion, our project demonstrates that computational optimization can significantly improve farmers' logistic operations. Thank you for listening and have a good day!